Got it. Okay, so welcome everybody. Happy Friday. Today we have our good friend Austin speaking to us about coding theory. He's going to give us a nice introduction to coding theory. So please welcome our speaker, and Austin, it is all yours.
Like this here thing in. All right, great. Howdy, everybody. So my name is Austin Dukes, in case you don't know me. I work in the area of coding theory. Wanted to give a little intro. I haven't taken a coding theory course at USF or anything, so I don't think that many people know much about it. At least a number of people I've talked to, are always interested in hearing about it. And I haven't really had a chance to sit down and actually tell them about it more than a few words, right? So I want this to serve as a very vague overview of the motivations, of the basic ideas, the basic notions of coding theory. All right, so hopefully it should be accessible to just about everyone. And please let me know if you have any questions. It's going to be rather informal, nothing incorrect or anything, but I don't want to just write definition after definition, stuff like that, because that's not going to give you a great idea of what's really going on conceptually. All right, so first I want to just mention a couple facts about finite fields. So if we have, let's just say a finite field is a field with finite cardinality. With finite cardinality. And so the most common examples, or the most probably simple examples, are ZP or FP, Z mod PZ, which are the integers mod P. Simplest example, but every finite field is actually somewhat.
And P is prime. Yeah.
And P is prime, yeah. That's probably important to write, huh? That's what the P is for, So, cool, admit. So I do see it. View, admit, perfect. All right, cool. So yeah, so for a prime P, Z mod PZ, the integers mod P, is a field, and it has finite cardinality in that there are finitely many elements in this field. All right. So some quick facts. Facts about finite fields. So one is that every finite field is actually going to have cardinality the power of a prime, or a power of a prime. So maybe I'll move this one down for a second. Let's say let F be a finite field. Then we have these properties. All right, so for one, we know that the size of F actually has to be P to the R for prime P and some R in Z plus, so some positive integer R. All right, we exclude fields of size 1. Or sets of size 1 as being fields. So it has to actually have a positive power of a prime. So when R equals 1, we have Z mod PZ. When R is greater than 1, we still have a field, but it's a little bit more complicated to write out in terms of the elements. All right, so in particular, R equals 1 is going to be convenient to work with by hand. Okay, so there's nothing wrong with fields of size P to the R for R greater than 1, but when we're working with stuff by hand, it's going to be a lot more work to just do the computations and even write out the elements explicitly. So R greater than 1, inconvenient by hand, but there's nothing wrong with it. So it's inconvenient by hand, but it's fine by the computer, or using some kind of software that can do the computations for you, just with the properties of finite fields, the elements get a little bit more abstract seeming. All right, so we're going to work with R equals 1 definitely the whole time. today at least. So last, we're going to say there is one field, there's one finite field, there's exactly, that's the whole point of this. So there's exactly one finite field of size p to the r for every prime p and positive integer r. And so with that being said, that lets us write for notation going forward. We're going to denote the finite field with q elements. Let's write let q equal p to the r. Again, p is always going to be prime, r is always going to be a positive integer. I won't really write r in the future, I'll just write q. So there's an underlying prime whenever you have q. All right. So for the number q equal to p to the r, fq denotes the finite field of size p to the r, q of size q. All right, and I'm saying the because I should have put up to isomorphism here. That was important. So I can call the elements different things, but how they work together. Up to isomorphism, there's exactly one finite field of every prime power order. So I'm going to call it the finite field of size q. All right. Get this out of the way. All right, cool. So that is really all we need to talk about with finite fields. Just some basic facts, but in particular, the prime power order is important because we're going to be working with finite fields and the elements in the field. And so we want to know what those elements are going to look like, act like, etc. All right, so that's all we really need for finite fields. Cool. Any questions? Let me know. So now let's jump right into coding theory. All right, so going off coding theory. All right, so coding theory is, in essence, the study of codes. All right. There are a few branches of coding theory that deal with different issues, or they're aiming to address different issues, but they all use codes to do it in some way or another. But the one that we're going to focus on today, the branch of coding theory that we're going to care about for today, be interested in, is error correcting codes. Or maybe just error correction. All right, so we care about coding theory today for the purpose of correcting errors. All right, and we don't know what these errors are occurring in. So for right now, just take it for granted that there's something might have an error and we want to be able to undo that error. Or we want to be able to still recover what was intended, even though something happened in the middle. All right, so let's think, let's have like an analogy. All right, before I go into the actual like vector spaces and math and everything that's complicated, let's get an idea of what's happening conceptually. All right, so imagine we have a channel from A to B. You can imagine that like you are A, all right, and someone that you're trying to communicate with is B. All right, so let's say us, and let's say like want to send message. And this is going to look like cryptography, this picture, but it's just an analogy. This is not exactly coding theory. All right, but it's gonna give some motivation for what we're doing. So, just as a side point, cryptography like historically was considered part of coding theory. I think it still is considered a branch, but the main goals of coding theory are quite different from cryptography overall, as of recent times. So cryptography, of course, has like a similar sounding application in that it's going to be involved with computers and all kinds of stuff like that. But overall, we're not trying to hide information. We're not trying to send information that's encrypted that someone else can't access. We want to send information that actually is extremely readable. That's the overall goal. All right. We're not worried about like adversaries trying to also read the data. Okay, so we're trying to send a message from A to B. So I don't know, this is our friend, I guess. And we want to send the message from A to B. Here is the channel. And ideally, we would say, okay, well, let's say the message is hello. We say it, and then we wait for it to be delivered through whatever this channel is. And then the friend hears us say hello. And they're like, hey, what's up? All right. That would be great if that happened every time. You can imagine maybe this channel is like a phone call. All right. But in phone calls, there's noise of some sort. So maybe like the signal is fading, or there's a lot of background noise or something like that. And so it's possible that what was intended to be delivered was not actually interpreted properly by the friend. All right. So maybe we say hello, but they hear hello. All right. Unfortunate. So we essentially want to address this issue in coding theory in terms of error correction of coding theory. All right. The error here would be these W's instead of the L's. Okay. And so now, how could we possibly address this issue? Let's keep this phone call idea, all right, but let's make it a little bit more concrete. Imagine you're on the phone with someone and you're trying to spell something to them, and they can't hear what letter you're saying, because maybe you're saying B and it sounds like D or B or E even. What would you do? Anyone have any ideas or examples of what would you do if you're trying to spell a letter to someone on the phone and they're having trouble hearing you, but you want to make it more likely that they're going to understand what you're saying? How would you like?
I would use the phonetic call sign alphabet. Like if I was saying A or B, I would say alpha or bravo afterwards.
Cool. So for example, A alpha. Say alpha. Cool. Any other ideas?
Repeat yourself.
Huh?
Repeat yourself.
Perfect. So if I say A, maybe I'll say A, hello, A, why can't you hear me? A, right? Just keep saying it over and over again. Both of those perfect examples of, in terms of an analogy of what's going to happen in coding theory. These are actually corresponds pretty well. This is two possible paths to go down. All right. So what's happening here is we're trying to guarantee that the information, so we start with information or data or whatever you want to call it, but it's original information. Okay. We start with information, which is A in this case, and we're trying to communicate it to the other party. But it's possible, or it's possible that they're not going to hear the A correctly. All right. So we want to add some sort of redundancy. Okay. We want to add redundancy so that we're helping ensure that the A is correctly perceived. If you hear the letter A 75 times, it's less likely that you're going to think that it was a B, for example. But if you only heard it once, maybe you weren't paying attention, you thought it was a B. All right. Same with alpha. We're adding literally more characters. So I want to send an A, but now I'm sending 5 different letters, all just to communicate one letter. All right. So we're sending more information, or we're sending more data than the original data that we're trying to communicate actually contained. All right. In some sense, we're increasing the message length. All right. So maybe let's just say repeat A, or we'll put alpha. There we go. And then the person over here let's say encoding. So we have some kind of process that's going to give us what we're going to communicate. All right. So the saying alpha, bravo, etc., is some kind of process. Repeating the letter over and over again is some kind of process. All right. And we are hoping that that reduces the chances of it not being accurately perceived, or accurately obtained. All right, so adding redundancy increases the likelihood that the message received is the intended message. Because definitely something will be received, but it's possible that it could be different, or maybe it's kind of like two different things and we're just not sure what was really said at all. We can't even make a guess. All right. So that is the idea of what's happening with error correction. We want to add this redundancy so that we can improve the likelihood that the message will be received. All right. So let's now go on to the somewhat informal, pretty informal, but more mathematically inclined definition of what's going on with a code. All right. So that's the idea and motivation of coding theory. And we use codes to do this. In a sense, the code is what, or not in a sense, but literally the code is what is received by the other party. And we have a message space in some sense of what we could possibly send and what could possibly be received. All right. And that's what a code tells you. So informally, we have, let's say C is a code. What that means is C is a collection of words. We'll put quotes around words. You could think of them as strings. We'll think of them as vectors shortly. A collection of words of the same length in this case. All right, so if I wanna have like an algorithm or an encoding process or a function or whatever you want to call it, that is implementable like in a computer, for example, with repeating letters, I'm going to say, okay, if I want to send a letter X, I'm going to repeat X 10 times. So every message that is sent is going to start with one letter and it's going to become 10 letters that are all the same. All right. So the code words, elements of C are called code words. So the code words would be strings or vectors of length 10. And the original words that we were trying to send are just single letters, so strings of length 1. All right. Cool. So now the thing is that we're using the word words, but we don't really know. I mean, to have a word, you have to have some kind of alphabet. You have to have an idea of letters. All right. So we need to define an alphabet to be able to say words. So we need an alphabet. And this is now where finite fields come in. We're going to define, we're going to call C codes are defined over finite fields. And over as in the alphabet of codes is a finite field of order q for some q. And in particular, fields have a lot of nice properties. Imagine like the real numbers, a lot of desirable desirable properties, but we can't implement, for example, the real numbers in a computer program in a lot of cases because it's not finite. Cool, go ahead.
So what was I going to ask? So when you say codes are defined over finite fields, you mean we consider the vector space over that finite field?
Yeah, so I'm
yeah,
give me like 5 seconds. Yeah,
okay.
yeah, 100%. So codes defined over a finite field. And now with all of these things on this page, I can finally write the definition formally, okay? And this hopefully will answer your question. So definition of a code. So a query code, think binary, ternary, etc. A query code C is a subset of f sub q to the n, which is the Cartesian product of fq with itself n times fq. This is n times. For some n, some positive integer n. All right. So a code is a subset of the vector space fq to the n. So it has n components, and each component is a letter or an element of fq. All right. So there's no other restrictions on C in general, though. A code is just a subset. Okay. The ambient space fq to the n is a vector space and has lots of properties. But just saying code with no other restrictions is just an arbitrary subset of that. All right. Cool. So that's the definition. And this n, it would make more sense to point to the n over here. We call n the length of C. So n is the length of every code word in C. So we just say n is the length of C. And the only other information that we need to write a code a little bit more succinctly is the number of vectors in the code. I don't have any restriction on what I can put in this subset because all I have is that it's a subset. So I needed some kind of information that's telling me how many vectors or words or whatever I have in the set C. So we'll say let m, that's m equal C. Cool. So I have the size of the set, the size of the code, and the length of the code, and I also have this underlying prime power. And with those three parameters, we can write a query code of length n and size m is written as, or denoted, I'll say denoted, a NMQ code. Cool. So just with those three parameters, we have determined not the elements of the code, but we've determined the main aspects of the code. All right. Cool. That is all we need to define a code without any other restrictions. So for example, let's see what is going on. Imagine we have the set 0, 0, 0 and 1, 1, 0. And we're viewing this as a subset of F2 cubed to the third. So we want to talk about what are the parameters of this code. What is the length? What is the size? And what is, what's Q? So just from looking at this code, how long is each code word in C? 3. So N is 3. How many code words are in C? I'll move this down a little bit. 2. Let's put M. And then Q is the underlying prime. So it's possible that Q could have been 3 just from looking at C, because I could have just not had any elements that use 2. But I specified that it's viewed as a subset of F2 to 3. All right. So that means that C is a NMQ code. Cool. And just to be clear, another example, N and M without any other restrictions are not dependent on one another. I can have N larger than M or M larger than N. They're not dependent necessarily. So if I make C the set 0, 0, 1, 0, and 0, 1, viewed as a subset of F2 squared, then C is a, the length of every code word is 2, size of the set is 3, and still the underlying prime is 2. All right, cool. So doesn't mean much like about what we're going to do with these as of yet, but that's explicitly what a code could look like. It's just a set of vectors in an ambient vector space, all right, over a finite field. Cool. All right, so we have to introduce a couple more concepts, and then we're ready to talk about some things concretely. All right, so we need to talk about what the weight of a code word is. So given C, in C, so given any code word you want, the weight of C, denoted by size of C, is the number of non-zero components. All right, so if C is 0, 0, 0, 0, 1, 1, then the weight of C is the number of non-zero components, so just 2. All right, so if you're looking at the code word itself, you just count up the non-zeros. And so that's a nice concept, but it lends now to defining a Hamming distance. I should probably mention quickly before I say the word distance that the weight function is a metric on C. Okay, cool. So we'll leave that for a second. We'll come back to it. All right. Put a little star. All right. So Hamming distance now. The Hamming distance of 2 different code words is what we want to talk about, or the distance between 2 code words. All right. And in this context, it's going to be Hamming distance. So given C1, C2 in C, we're going to call it H because D is going to come up later. We are going to denote H of C1, C2 as the Hamming distance, and it is going to be defined as C1 minus C2, the weight of C1 minus C2. And so now I can change this. I got excited and just started writing stuff. The Hamming distance is a metric. So by C1 minus C2, I mean we take every component, the first component and the first component, and subtract them. Second and second, subtract them, etc. So Hamming distance of 0, 1, and 1, 1 is the weight of 0, 1 minus 1, 1. And that would be So if we're looking over F2, 0 minus 1 is 1. So it's 1 comma 0, and that is 1 because there's one non-zero component.
So this
All right.
is well-defined distance focused on the entire F2, yeah?
Yes,
Right.
yeah, for sure. And C is, yeah, just not necessarily the whole thing. But definitely it's a metric on, or it's a distance function on the whole thing. Given n, of course. All right, cool. So that is the idea. All right, but now we can write the Hamming distance in a little bit of a more intuitive way. All right, so instead of actually doing this subtraction and just counting the non-zero components of whatever we get after subtracting, what we're really saying is if the component in the end is 0, so for example, this one was 0, how did we get 0 when we subtracted them? It's because this component and this component were the same. All right, and then how did we get a non-zero component? It's because this component and this component were different. All right, so if we're counting up the non-zero components of C1 minus C2, that's exactly the same thing as note H of C1, C2 is the number of components which differ between C1 and C2. And so that kind of makes things a little bit nicer, just visually. We can just line them up side by side, see how many are different, and that's our Hamming distance, all right? And last little thing, we're going to define D of C. D of C, define, to be the minimum distance of a code C. So given a code C, define D of C to be the minimum distance of C. And so what I mean by that is we have D of C is we want the minimum possible weight of C1 minus C2. By definition, Hamming distance is the weight of C1 minus C2. So we want to go over all the possible pairs of code words, minimum non-zero. This is important. Because if the 0 code word, or if I take any two code words that are the same code word and subtract them, I'm going to always get 0, 0, 0, 0, 0. I'm always going to have weight 0. So every code, as long as there's any code word in the code, will have minimum weight 0. So we want something that's not trivial, all right? Something that actually tells us something useful. And so we're going to take over all the possible pairs of code words in C that are distinct. So with two separate code words, two distinct code words, we want to count the number of 1 less than equal to I less than equal to n. We want to count the number of components which are C1 I not equal to C2 I. So the number of distinct components between these, or equivalently, the minimum with the same situation of the weight of C1 minus C2. All right, now we are ready to do stuff. So this D of C is the minimum. We're going to call it the minimum distance. It's implied that it's non-zero. Okay, it's D of C, but once we know once we're given a code, there is a minimum distance, and we're going to call it D. All right, perfect. So now we're going to move into linear codes, and this D of C is going to have it's going to have at least one nicer property in a linear code. All right, so given an arbitrary code, this is a calculation. I have to, in theory, take every possible pair of code words, compute their difference, find the weight, or like compute the number of components which are different. But either way, I have to go through every pair a priori. All right. But with a linear code, that's not the case. So linear codes, a code C is linear if any linear combination of code words in C is again a code word of C. Let me say again, I guess. So any linear combination of code words is still a code word. All right. For example, if I take 1, 1, 1 plus 1, 1, 0, that's a linear combination of two vectors. Let's say that they're in the space, they're in C, which is considered a subset of FQ or F2, 3. So if I take this combination, I'm going to get 0, 0, 1. And if C is linear, then this element is guaranteed to be in C. All right. And so already I know a lot more about the elements with this assumption, because once I know two elements, I know a third. And once I know the difference of two elements, I know a third. I can multiply elements by a scalar, I know another element, etc. All right, so I have definitely some more structure in this code immediately, okay? And in particular, this is equivalent to saying a linear subset, or a subset that's closed under linear combinations, subset of a vector space, is a sub-vector space. So C is a subspace of FQ to the N for whichever Q and N C is considered over. All right. So once C is linear, it's a subspace, and now we have lots of nice properties about C. All right. In particular, the distance, the minimum distance of C, we said it is the minimum for a distinct code words in C. It's the minimum Hamming distance, C1 comma C2. Another way of writing the same thing as on the other slide. But this is the minimum of the difference between them. And I know that when C is linear, this difference is still going to be a code word of C. All right. For an arbitrary code, the difference is not guaranteed to still be a code word. It's definitely a vector of the same length, but it's not guaranteed to be an element of C. For a linear code, that is guaranteed. So this is in C. So I can actually write this as the minimum. So maybe I'll write this one more time. C1 not equal to C2 in C. So I'm looking at the minimum weight of a code word in C, because I know that C1 minus C2 is, I'm just going to call it C. Let C1 minus C2 just be an arbitrary code word of C. And I'm going to go over all the possible code words. So all the different things I can get back from C1 minus C2. And since they're distinct, I'm going to take any code word that's not 0. All right, so it's the minimum weight of all the code words of C. It's the minimum non-zero weight. All right, and so that already makes our life easier. Instead of having to go over all the pairs of elements, we only have to go over all the elements. So definitely that makes that computation easier. Okay, and we have lots of nice other properties with linear codes, but in particular, this one's easy to see. All right. Also, the size of C. So we had M is the size of C. In a linear code, because C is a subspace of FQ to the N, we can actually write that M is Q to the K for some K greater than or equal to 0. We're not going to want an empty code. We're not going to want a 0, not an empty code, but the trivial code of 0, 0, 0. But we could have it. It could only have one element. It's not going to be very useful, but some subspace of FQ to the N is going to have size Q to the K for some K. And so now we have distance, we have the size, and the length is not going to change between a linear and nonlinear code. They're still going to have vectors of the same length. So a linear code, we're going to denote it a little bit differently because the linearity assumption is a really big one. So we're going to denote it by brackets NKD sub Q. All right, so with those parameters, as discussed before, a linear code with length N, the size of the code is Q to the K or of dimension K, and minimum distance D over FQ is denoted by an NKDQ code. Cool, perfect. So that is what we got for setting up codes. What we're talking about subspaces of vector spaces. The alphabets are finite fields of size Q. Distance of code words is the number of components that are distinct between them. And we are starting with messages or words of length K, and we're ending up with words of length N. All right, so C is a subspace of FQ to the N. C is going to be isomorphic to FQ to the K, and it's a subspace of FQ to the N. So we are taking words of length K and embedding them. In the space FQ to the N. I guess words length N. All right, and so N has to be at least K, obviously, or else we're not embedding it anymore. But if N equals K, I'm not getting anything new. I'm essentially just copying the word over. All right, and what we're going to want with respect to the ideas of adding redundancy over here, with respect to adding redundancy, saying more than we are actually originally trying to say, but with the intention of communicating it more successfully. We're going to want N to be large compared to K. We want to not make N too big, but we want to definitely make N typically bigger than K to actually add that redundancy. All right. And N minus K is the redundancy of C. Yeah, go ahead.
So N is somehow representing like the amount of redundancy you have for N minus K.
Yeah.
Q has some more, yeah? Like, so the bigger Q, you pick the more characters sometimes you represent. Is it better to pick, is it better to pick large Q and smallish N, or small Q and large N, or is it dependent on the problem?
So it depends. There are definitely like relationships between N and Q, but overall the main, arguably the primary focus is the relationship between the parameters N, K, and D, and Q doesn't really have an impact on it for a surface level reason. So the alphabet is not going to change the dimension of the space. It's just going to change the size of the space in the bigger space.
I mean, so for a computer though, Q is 2.
Yeah.
So my question is why
often, but you also have
my question is why
hexadecimal.
Yeah.
Say what?
Anything but 2 A's. Why consider it?
So also powers of 2 are also implemented. But you also can implement non-binary things. Yeah, but you also don't need binary for it to be implementable. Binary is the most widely used, but it's not the only one.
So my question is more like what practical uses have it? If that is a good question.
Yeah, so depending on the characteristic of the field, so depending on the underlying prime, you have a lot of like different, not a lot, but you have different situations going on with the properties of the codes of the field and other situations that are a little bit.
So the answer is it depends.
No, it's just a little bit like more involved than like just from this definition.
Yeah. Okay.
There's no reason to not work with q equals 2 every time. Just because that's simple. Why not keep it simple? The idea of making q larger is. Yeah, go ahead.
May I say something? So usually you want Q a little bit larger because you achieve a better distance. So that's one of the reasons you might want to enlarge Q and not consider Q equal to.
Yeah. Like, so for example, if we had 0, 0, 1, 1, 0, 1, and 1, 0, if I take a sum of these elements, I'm going to like anytime I have 1 plus 1, and anytime I add 2 non-zero components, it becomes 0. If I have q equals 3, so this is q equals 2. If I have q equals 3 in the same vectors, if I add 1 and 1, it doesn't become 0. And so, yeah, and so that is probably a simple way of seeing what he just said. All right. Typically, or the most fundamental bound, arguably, is the singleton bound, which I'm just going to state, and we can prove it next time in a million years. Yeah, love that, locked in. But the surface level bounds are not going to involve Q. All right. So just write down the singleton bound. And with this, next time, we'll talk about actually the idea of error correction and error detection, and then prove this bound and see how all of these things are going to come together in actual applications of codes. All right. But it's hard to go over an application when we don't have the same language, as always in math. So the singleton bound says that k is less than or equal to n minus d plus 1. And roughly, like very, very informally, or very quickly rather, if you take a word of length n and you remove the last d plus 1 or d minus 1, sorry, components, what's left has length n minus d plus 1. So overall, it has length n. You remove d minus 1, you get something that has length n minus d plus 1. And because d satisfies that the difference between two components can't be smaller than d, because it's the minimum distance, unless it's the same code word, we end up with a bunch of distinct code words in the beginning of every code word. But we only can have so many of this length. And that's essentially how you prove this bound. But that was, a very like hand wavy approach. So next time we will talk about the real applications, but hopefully this served as a useful introduction to coding theory, the language, and the notions of what we're going to be talking about.
All right, so I guess
cool.
Everyone can hear me, yeah? Let's thank our speakers. So are there any questions?
So did you mean to say that a given k and d specifies like a particular code?
No.
Or there's like lots of codes? Okay.
Yeah, it specifies the gist of the code, I guess I would say, like informally, but it doesn't specify what actual elements are in the code. No. So there's lots of
Well,
spaces of dimension k in fq to the n when k is less than n. There's lots of distinct subspaces. So definitely just saying I have dimension k doesn't tell me which subspace I'm actually talking about.
I guess I was asking if they're all like isomorphic in some sense.
100%, yeah, for sure.
Okay.
But if we're talking about like implementing a program or an algorithm in a computer, we're going to want to know, given a word, what should we actually end up with as our code word that corresponds to it. And so we're going to be in a specific subspace, but definitely they're all isomorphic, and I could encode the same information with nk and d lots of different ways in general. That doesn't change anything about how much information I'm actually transmitting and how much length I actually have to use.
So any other questions from the audience? Let's encourage people one more time. Unless we're waiting for another talk next week, we'll be done for the semester, and then we'll pick up next semester. You can get the first talk.
Cool.
So
Can't wait.
thanks everyone for coming. See you next week. Can you click stop recording?
Thank you.
Thank you.